Casper and Leon, and today I will talk about cell-probe lower bound for the succinct Boolean matrix vector multiplication problem. So today in the morning, Amrutpadev already talked about some matrix vector multiplication problem, and we have seen some lower bound. So again, let's recall what the problem is. We are given a n cross n Boolean matrix, just 0, 1 matrix, and our goal is to first preprocess M and store it in a data structure such that at later point of time, if I am given a n-dimensional vector, say V, 0, 1 vector, I should efficiently compute the value MV. And here, of course, I am just considering this product to be over Boolean semi-ring, so that means I just replace addition by OR and multiplication by AND. Okay. Of course, you people already know, but still let's see that. This is just say an example. So this is a matrix M and say V, and to calculate this, I just compute just end of each of this entry and then take OR. And so let's talk about a little bit about what's the motivation behind studying this problem. So this is actually a special case of online matrix vector problem, also known as OMV. So where we are given a matrix M, again Boolean matrix, and there is a stream of vector coming one at once, and our goal is to compute MVI, but we cannot see any vector that comes later point of time. And it is conjectured that even there is no randomized algorithm that takes truly subcubic time can solve this problem. And this is actually known as OMV conjecture and well known in the harnessing P domain and introduced by Henginger and others in stock Fictune, I guess. And what is known so far? This is a result by Larsen and Williams that show that OMV can be solved in n cube over 2 square root log n. So this is not a truly subcubic time. So that means amortized time is n square over 2 to the square root log n. So this arises the question, so can we show a cell probe lower bound? Because this is a data structure problem. We have lots of tools in our hand. There are lots of results in cell probe data structure. So can we somehow show?
It's an upper bound?
So this is an upper bound. And so can we just give a matching lower bound? So this is the question. So by cell probe model, we have seen lots of results today that we just charge for the number of cell access. So computation is completely free. But unfortunately, the answer is no. We cannot show. And this is also by Larsen and Williams. So in the same paper, they show a data structure, cell probe data structure that has query time n to the 7 over 4. Up to some log factor, polylog factor. Okay, so that means OMV conjecture is false in cell probe model. But still, we can try to show some lower bound. And also it remains the question that what's the true complexity of this problem. So we study further and we actually achieve a query time order n to the 3 over 2. But the point is that our algorithm is randomized, but previous Larsen and Williams algorithm was deterministic. And what we show is that our data structure will look like something. We'll store the input matrix in a read-only memory, and then we also have a extra order into the 3 over 2 bits. So this is the redundant bits that we store along with this input, and then whenever some query comes, we'll probe in this data structure the whole thing. And so this type of data structure is called systematic succinct, where we actually store the input and also a small amount of redundant bits. Okay, so before going into the lower bound, so I mean what we proved, so let's just do some warm up. So actually it is easy to see that any data structure that support this MV query, so that must have say T must be, I mean query time must be greater than N. I mean it is very simple, easy to see, but let's see it. So just consider the N elementary basis vector where the just in a vector, so just the say first bit is 1 and second and so on. Say in this example, so this is the dimension 5, so there are 5 elementary basis vector, and what is the value of mi, ei? So this is basically the ith column of M, and so this is just a pictorial view. So this will reveal the first column, so this query. So as a result, if I can answer my MV query for all these query vectors, then actually I can get back the whole input matrix M. And so that's why we can get some information theoretic lower bound in this way, that we just choose M uniformly randomly, and so the Shannon entropy is n square. Now we can just encode the content of all the cells accessed during this process of answering M of EIs. And how do I encode? We just append the content, say first, I mean there is arbitrary order, so in that fixed ordering, whatever it addressed, I just write the content of the cell.
Okay. I think what is the assumption on the space? How many redundant bits are you assuming?
Okay, so here we are not consider. So this is just a, I mean warm up. So I am just considering any data structure.
But I don't understand. If I store all of the queries, all of the answers, that's like exponentially many.
So
my query time is 1, or what?
No, you still need to, because you need to output the vector of length n.
yeah.
Okay, so that's a different one. It says that the output size is.
So we are just considering this MV problem,
So
right?
saying regardless of space, I need.
Yeah.
No, I think you were right. I mean, if we store all the answers, then.
No, but we still have to prove that answer, right? So that is already a n-bit vector. So that.
Isn't that a simple?
What's the word size of the model?
Huh?
The word size is a bit, right?
Yeah. So okay, here for simplicity, I'm just considering what size is bit.
But if the word size is a bit, then the explanation is much simpler. The answer size is n. So
Yeah.
that's it. So it's
Okay. Okay. So this is
That's not an explanation, because what if you can get it out of nowhere? You just don't need to read it. Like, I mean, it doesn't mean that you need to read n bits. I mean, without this argument, you cannot, even with.
yeah.
sure. Okay.
Okay. Okay, so this is the story. So basically encoding length is Tn. So say in the worst case, query time is T. So for answering n vectors, I need Tn encoding length, and so Tn should be n square, and that's why we'll get T is greater than n. Okay, so now let's come to our result. So what we show? So we studied this lower bound problem in the succinct data structure model. So basically, we have this restriction that our input matrix is written on a read-only cell, and then some extra redundant bits, say Rn amount of bits. And okay, so we slightly further generalize that, okay, so this extra redundant bit, so this I can access any point of time. So we will not charge for that. We will only charge for accessing any bit from this input matrix. So clearly, if I can show a lower bound in this generalized model, then that will still hold for systematic succinct case. And what we show is that if the length of this bits, so this is say greater than n and up to say n square by 4, I mean this is any constant, so then r times t have to be greater than n cube. So there is a trade-off between this amount of redundant bit and the amount of cell probes that we need. So and our second result is that if Rn is less than n, so then we have to probe almost all the entries of the input matrix. And this is just a corollary of this first one. So this is just using a very simple padding argument, so then it follows. Okay. So now for the remaining part of the talk, so let's try to give a proof overview of this theorem. So for the proof, I slightly simplify the statement and I'll say that, okay, I will not prove this trade-off, but instead I will say show that if R is less than n to the 3 over 2, then query has to be greater than n to the 3 over 2. And just believe me that the same proof will work. Just we have to set some parameter and all. So here is the proof idea. So first we will define a hard distribution on the input matrices, and then I will select a special type of revealing queries so that this query can reveal actually lots of information from this input matrix. And then again, just like in warm-up example, so we just encode the bits that probe during these queries. Okay. So now let's try to define this hard distribution. So here is what we will do. So we first divide this matrix. So each row we will divide it into blocks, and each block is of length 2 square root n. So how many blocks are there? So there will be root n over 2 many blocks. And now I will choose uniformly randomly, I will choose exactly one entry from each of these blocks and set it to 1. And I just set all the remaining entries to 0. So basically in our matrix, so in the each row, so there will be at most root n over 2 many ones in each row. And it is easy to show that, I mean, this entropy of this distribution, this is n to the 3 over 2 log 2 square root n, because there are that many blocks, and for each block I have to specify this position of this. Now similarly, let's try to construct the revealing queries. So I will design 2 square root n many query vectors, and in the following way. So in the vector also we'll just divide it into blocks, just as in case of this matrix, and these are also of size 2 square root n. And now in the vjth query vector, what I will do, from each of this block I will just look into the jth position in each of this block, and I will just put 1, and remaining I will just keep 0. So now let's see that how this answer look like. So suppose given, I mean, I just choose my query vector from my this revealing query set, and now say the answer vector, so this ith row entry is 1. So how many such query vector can be? Can anybody say? No, you're not allowed. Don't laugh. Okay. Since there are actually in each row, so in this matrix there are square root n over 2 many ones, so at most this many query vectors can make this entry 1, and for the remaining it has to be 0. So there are at most square root n over 2 many vectors for which this guy can be 1. And now see, so if suppose this guy is 0, so then actually I learn a lot about it, about this matrix entries. And what we learn, so basically we learn that if say vjth on vjth query, so this is 0, so then that means in all this jth position in this guy, I mean in this matrix, they all are zeros. And since I know that for 2 square root n minus square root n over 2 many vectors I have this 0, So that means for each block, I know that many positions are 0. So if I can answer all these queries, then actually I learn a lot about from each of these blocks. And how much I learned, so basically given this set of answers, so actually now entropy drops to log of square root n over 2, because these are the positions that are still undetermined. So my 1 can be in any of these positions. So now just try to use the encoding argument. So given this answer, so how much information it revealed? So basically previous entropy was this guy, so the difference is n to the 3 over 2. And how many queries I answered? I answered 2 square root n many queries, and say the worst case bit probe was t. So to answer all the queries, the total number of bit probe will be at most 2 square root n times t. And now just like as in warm up, just append them and encode it in that way. Just append all the contents. So what we get? Okay, so and another thing is also that you can also encode this R, because using R and all this probed from the input matrix, I can get back all these answers. So my encoding length is R plus 2t square root n. And since I know that R is less than n to the 3 over 4, 2 by 4, so what we get? So we still get t's. Okay. We are still in a bad shape. Okay. What we will do? So here is the fix. We will use a clever encoding. We will not just append all the contents. Instead, what we do? So this is the clever encoding. So don't encode all the probed entries, but instead just encode all the 1 entries just. Because if suppose from the encoding I can get all the 1 entries, I know that whatever remaining probes, that must be 0. So just encoding 1 entries will suffice. And we just encode this 1 entries of all these query vectors. So say this is a k, so these are the set of all 1 entries. And just encode as a subset of all the probed entries. So there are 2t square root n many probed entries, and now just encode this subset. So for that I need log of 2t square root n, choose k many bits. And okay.
Just to understand, the 0 entries, you don't even encode the addresses?
No.
I see.
Just for the.
But you know that the answer.
Yeah. So if my while simulating, if I answer
so you know that literally
all of them are, yeah. Since my query vectors are fixed, I know that these are the only query vectors possible. Okay. So this is my encoding length now, and this is greater than this guy. So just one thing, just recall that when we use that given this answer, so then we do not have this extra k factor. This now comes because now we actually learn those 1 entries, because I encode those k1 entries. So that means I know that I explicitly know where these k1 entries are in the input matrix. So these are the extra laws that we have. But now if you just massage this thing, so then actually believe me that you will get t is greater than n to the 3 by 2. I mean, these are just calculation, nothing else here.
So you're encoding better the query or the output?
Sorry?
Are you encoding better the query or the output of the...
I still don't understand your question.
Okay. Never mind, I will ask you.
You want to what?
The entries of the matrix are not balanced.
The sparse matrix.
Yeah, these are sparse matrices. Okay, so do I still have some 5 minutes time? Okay. So if that is the case, so then let's talk about the upper bound also. So how do we get this upper bound? So just recall that we achieve this amount of redundant bit is order n to the 3 over 2, and the query time is also 3 over 2. And this matches this lower bound. Okay. So for the preprocessing phase, what we do? We just enumerate over, so given this matrix M, we enumerate over all the submatrices. And we just find all the large submatrices with sparse row. What do I mean by that? So by large submatrices, I mean that submatrix that cover the uncovered matrix, so n to the 3 over 2 entries of the uncovered matrix. And by each row making sparse means in each row I have this one entry density is less than 1 over square root n. And now I just list down all such submatrices, and also I encode all these 1 entries. So how many submatrices I have? So I have submatrices at most square root n many submatrices because of this restriction that I just store large submatrices, and for storing each of these submatrix I just need 2n bit at most. And also to encode all the 1 entries, I know that each of my submatrix that we actually store for them, for each row this is sparse. I mean sparse in the sense of 1 density is very small. So that means to just encode all these 1 entries, I just need at most n to the 3 over 2 bits. And this is just my preprocessing step, and this is what I store as a data structure, this redundant bit. And now while doing the answering the query, what I will do, so just given a query vector, so from this matrix I just first of all I discard all these columns, so where the corresponding entry is 0. And now I just consider all the submatrices that are encoded in this redundant bits. And now for each of these 1 entries in this query vector, I just see that whether there is also a corresponding 1 entry in my encoding. Because remember that, recall that in the encoding I just encode all the 1 entries also in those submatrices. Say here, so I find 1, so there is 0, say here 1, I find 1. So for each such I just set the corresponding in the answer vector, I just set it to 1. And I keep on doing that. And when I am done, so there is no such 1 entries left in my encoding. So what I will do for the remaining rows from this uncovered part of the submatrix, I just sample square root n many positions. And for those sample positions, I just check if there is a 1. If there is a 1, I just set the corresponding bit to 1. And the thing is that since I know that in my encoded part, so I actually store all the submatrix that has 1 density small. So I know that either here this uncovered part, the 1 entropy, 1 density must be high, and in that case with high probability I will find this 1, and otherwise the uncovered part, so this size is very small. And in that case, actually I just read all the remaining portion of the matrix and then just decide on the answer. That's what. And so let's now come to the open problem. So as you see, so we just could show the lower bound for the systematic succinct case, but it is still open that for non-systematic, what can we show? It is not clear from our argument that whether we can at all generalize to non-systematic case. And also another question that actually Arkadev talked about in the morning, so this is the UMV problem. So where Larson and Williams show that probed entry is n to the 3 over 2 and redundant bit is n to the 3 over 2, but we don't know any such matching lower bound. what actually we can, so just with some small idea along with this warm up thing, so we can actually show that t is greater than n over log n. We don't know that whether this is the correct bound or not. That's all.
Any questions?
So right now you have the succinct. In your encoding, you're sending all of these extra arbits, right?
Yeah.
So, but that's not, I mean, because you're giving those pros for free, right?
Yeah.
But what if you just sent the locations and just the contents of those things that you probed? Can you extend like to maybe
No, at least our result don't extend to give a better result in that case.
So it seems like you learned a lot of information every time you got a zero entry. If instead of doing this problem over the Boolean matrices, you did over some even maybe small finite field.
Yeah, so okay, so actually I just choose to remain silent on that. In our paper actually we also considered this UMB problem over F2, and there actually we also show the similar lower bound for the UMB problem, so this is much harder than MV. So there also we show that RT is greater than NQ over log.
Just thank Diptarka again.